starting showing. Oh, I forgot to wait about that. Okay. Okay, so I will start with a short presentation, something about a bit what is CFD, what's are the advantage of sensor CFD, then a small session of question. Usually people wait a bit later for the question. Then I will present some case that are already prepared. And I will also show you how to draw something, to draw a case. The case I will show you is the one that is displayed just there. It looks scary, but it's not that scary. It's in our instruction manual. So I will put it on the chat, the instruction manual. So let's start. So what is computational fluid dynamic? Computational fluid dynamic is the use of computation and the equation to solve how the fluid are displaced in a volume. And the heat and the species that come with that volume also are computed. So it's true physics. It's physics that's existed before computing, not computing, before computer. And it was computed by hand before. Right there is a computing room with a computer, people that has the title computer that was computing the element for the wing, for the NASA. I think it was not NASA at that time, it was NACA, something like that. Anyway, so it's real equation. It's not a black box. It's real physics. It's things that we know. The numerical method that are used were existing before computer. We just use computer now because it's much quicker. And yes, so the CFD that I will present today model all the important physical phenomena that you have in data center. So you have the momentum, the heat transfer. We also have turbulence and buoyancy. So everything is in the model. So why you want a computational fluid dynamic? Computational fluid dynamic is an analytical tool, so that allow you to see what's happened far from your probe. So you have probe on your rack, you have probe on your crack, and you don't want to put probe in your vent, put probe at the door, put probe everywhere. You don't want to put an anemometer. Anemometers are really expensive. You don't want to put that everywhere. But you can use computational fluid dynamics to compute everything that is far from your probe. It allows you to understand how the air circulates, how the mixing, where the mixing happen, and the origin of your low performance for your crack or your rack. So you can see every inch of your data center. You have some case, for example, that you have a really, really well contained, really beautiful data center. Everything seems perfect, but at some place you have air coming back to the crack instead of going to the rack. You can see that with the CFD. Okay, what is sensor CFD? Sensor CFD is the easy way to use CFD. So it's come with AKCP Pro Server, and you have all the tool for data center. So we have rack, crack, and vents, and everything is already programmed for you. So the boundary condition, which are really important in CFD, are programmed for you. The conduct are programmed for you. You just have to slide the rack, slide the crack, set the boundary condition, set the value, but you don't set them because that's the sensor part. The sensor part. I will come to that. So yeah, you have specialized drawing tool that's already use the software maybe that's you are using from years. And the other advantage is that we use the probe and the sensor that you have on your rack and on your crack. So you use the live results that exists in reality to bound the CFD model. It means you don't have to go and measure each place and then the condition change and do it again. You don't have to guess any measure. You have no mistake about the conversion unit. And yeah, it's entered in your CFD model automatically with one click of a button. It's so sweet, so easy. And I think we are the only one that offer that kind of process. So usually when you do CFD, you got a lot of job. You got the drawing step. The drawing is kind of important, and we cannot really remove it because we want to know what you want to model. And then after that, you have to do meshing. And meshing is the action of separating the space in a small piece to do the computation. So you remember the people that was computing, but they compute small element of the volume. It's really hard for a plane that can take up to 3 months to do the meshing. So it's really important step because it leads to numerical error and problem with the model. Then you have to configure your case, the solver you will use, the boundary condition, all the equation will be split. And then after that, you do parallelization. Then you can, in the end, run your model. Once your model is run, it's not finished because you want to see what happened. And you need to do some processing. And in the end, you can enjoy it. So it takes years of learning, years of experience. It costs a lot of money. Some software, professional software costs a lot of money. And you need good computer and good knowledge. So sensorCFD just remove something like more than half of the step. So now you draw, you run, and then you have your result. And the best is that you don't have any trade-off because we use finite volume method. We use a beautiful mesh, hexahedral mesh. It's just that it's made for you with your drawing. So you send it and we draw the meshing, we do the meshing, we do everything. And it's a real CFD toolkit that was subject to the thousands of publication. So there's no cheating, there's no shortcut, it's the real stuff. It's just that it's automatized for that case, for your data center. So yes, that's about CFD. That's about sensorCFD. I will present a small case in a few minutes. If I have question, if I don't have question, I will go straight to it. So do I have some question? No question? Okay, so let's prepare a case. So the case we will prepare is in the instruction manual. If you go in the chat, I sent it to download. So it's page 13. So all the steps I will show today are in the instruction manual. So it's exactly the same. So let's start. Okay, so I will start by showing you how to start a droplet or a virtual machine on the cloud. So if you don't have any powerful computer, you can use cloud computing. If you have your own computer, you can install sensorCFD on a server and connect it with AKCP. So the only difference today is that I will use a computer on the cloud, but you can use your own computer. So I go on DigitalOcean. I find DigitalOcean way more easy to use than Microsoft Azure or Amazon. But both are easy. Both you can use both also. You don't have to use this one. So I will create a droplet, which is a computer. I will take someone close to me. I go to market, and that's the trick. The trick is to use Docker. So Docker will get the image, sensorCFD image, and install it on your computer. If you want to install it on your own computer, it's the same thing. If you have Windows, you can install Docker on the Windows and download it the machine and it will work. If you have Linux, you just download Docker and it will download the machine. So I will continue the step. CPU, because we want to do a lot of CPU tasks. So that's the password. So CFD demo. I think he doesn't like it. Voilà. Right there, create the play. So it will create a computer. Like I just told, this is a normal computer. It's a Linux machine that we start. So all the following step is the same for your computer that you will use. The only difference is that the Docker is already installed in the machine that I'm starting right now. So once it started, I will just go here. That's the instruction manual I just shown you. And I will take that magic line. That line will do all the job to install sensorCFD on your machine. So I will connect myself on the virtual machine. So right there. No, that's not what I want to pass. One. So there. That's not the right one. I'm sorry, everyone. I tried to go a bit too quick. Here we go. Okay, so now I'm on a brand new computer. I never went. The only thing that it's installed is Docker, and I will copy and paste the command line that I just showed you. That command line there. Is the font too small, or it's okay for everyone to see? So I enter the line, it return, and it download everything. So it's download about 30 gigabyte because it's a machine, it's a whole machine. So with drawing software, with CFD software, with our software that we just made, so it's take a few minutes. I already have one install and started. So I will go in AKCP, APS server. So to start using CFD, you go in menu, setting, server setting, CFD simulation. If you never did anything with CFD, that's what you will see. You click right there to activate it. It's a free module, so you don't have to pay anything. It's already on your APS server if you have one, the latest version, obviously. So that is the IP of my computer from DigitalOcean. So that's the one I started before the presentation, this one right there. The number of CPU, the port, and the number of steps for the simulation. So ideally, the larger, better, but it's really long if you put a large number. So you click on save, and you are ready to use CFD. Okay, so now we are the drawing step. So it started, it will start soon on our new computer. We have our web interface. I will just start drawing. So add a data center. I will name it my cool data center because everyone wants a cool one. So in those setup, I will set the width of the room, the length of the room. They are both 6. So I'm following the map again. If you download the manual, I'm following those instructions. So if you want to try yourself later, you just use the manual or listen to the video. I think the video will be posted on YouTube also. Okay, room width, room length. After that, the ceiling height and the floor. So I set a false floor and a false ceiling because in that demo, I want to switch between hot and cold quickly, but you don't have to. So I will put the height of my rack, 1.7. So. I did something wrong. Okay, the floor is 0.4. Sorry, everyone. Next. We will async the rack later. Nicola will show you how to do it. So I say later and finish. So we have our drawing software. To start working, we click on the lock right there. If it's blue and empty like that, you can edit it. And then on the pen and map editor mode. So I will start by placing the rack. So for the demonstration, I use the default size, but if you want to change the size of the rack, you right-click edit. So you can change the length and the width, even the height. So right now we are doing cold containment. So we want the front in the containment and the back pointing outside. So we will place the rack exactly like in the plan. So 1.8. You can use the arrows from your keyboard to place the thing more easier, with more ease. Sorry, more ease. My English is missing sometimes. Okay, like that. And then you can activate snap to object, which make the life so much easier. You make a copy of your rack. You don't do that. You make a copy of your rack and you move it and you snap it like that, like that, like that. So we have our first row. It was that easy. Then click on containment and we place our containment approximately. So I would just edit it to be sure that we have the right width, 112, and the length is good. Save, and then right there. Be sure that you have no space between the rack and the containment, or else you will have some problem later with the model. So like that, I flip the rack, and again make a copy, snap, make a copy, snap, make a copy, and snap. So I built my column. If you want, you can use the automated setup in the GUI I just use. Right now, we are doing cold containment, so we want a cooling unit that goes from back to bottom. So it's that one. Right there, I will set the dimension. And rotate it to so it faces that direction and place it exactly like the map. If you try to make the same room, it's not important that everything is the same value. It will work anyway. It should work anyway. If you don't, tell me and I will find why. Make a copy. Flip. And then I adjust it more precisely. 64. And so we have our cooling unit, we have our rack. The only thing we are missing is our vent that we want to put. So I will just draw it like that. Edit, put the dimension. I think it's 0.4, 0.4. Save. Put it in the center. 26, like that. Right there. Okay, so we didn't put the start the simulation right there because the good habit is to see what you did in 3 dimension to be sure that everything is set like you'd expect. Right now, I put the vent on the top of the crack, which is not what I want. So I will go back in 2D. And we go there, move them on the floor, right there, move them on the floor. If I go in 3D, here we go. We have our cold containment setup all ready to be modeled. It didn't take more than 5 minutes. It was quick. If it's not 5 minutes, it was really quick. So I think I put the ceiling a bit higher than usual, but it's not bad. Okay, so to start the simulation, you go in 3 dimension, you click on the pen, you go on run CFD simulation. Next. So right now, we don't have any probes. So either we try to guess the temperature at the inlet and outlet, we try to guess it, or we load the sensor, the value from the sensor. So if you have your setup in reality with the probe, you can click on load value from the sensor, okay? And it will bound the simulation with the reality. That's really, really an important part. But since we don't know it, I go in set default. If we have right now a perfect containment, so in theory, the temperature would be the same at the out of my cooling unit that goes in my rack. So next, then you set the power. So here again, you have either our probe or it will work with the other probe also to get the power that goes in your rack, in your crack, and you can load them directly with the boot button right there. But we don't have it, so it doesn't work. So we have to set them. So we have 42 units, 42 blade on each unit, and the computer are running like crazy because they are doing CFD. So they use all available power. And we have our cooling units that are sufficient. So we have a steady state. And we click on next. So with the delta T, the delta the temperature and the inlet in the outlet, and the power used, we can compute the air velocity going through the rack. It's the trick of hot wire. So if you already heard about the hot wire sensor, it's the same trick we use. We can compute the velocity with the heat that passed through your rack. So finish. Are you sure that you want to start the simulation? Yes, I'm sure. So, okay. And it started. If we go look on our server, so that's the one I just started. Finish is ready to be used. But I will look at the new one. Sorry. So it's starting the simulation. So we see that we are making the background mesh. And the simulation will proceed like that. It's take for that model about 40 minutes for the setup computer I just rented. So like in the cooking show, I will take the one that is already ready and show you the one already ready. So here we go. Once your simulation finish, you have your drawing like that. Don't forget to put your lock back, or else you will change position of things and it would be sad. Okay, so you have a lot of CFD layers. You have for the temperature, for the velocity, and for the pressure. The one that are really nice to see with that kind of configuration is the airflow on X, no, on Z, on X. Okay. A trick, if you want to see more clearly, you go on the pen and use single rack. So it's a view that allows you to see just one rack at a time. But if you don't have any rack selected, it's hide all racks, so you can see all the air flowing around. Really pretty neat. So we see the air going under. So I go back here. If you lose your action panel like I did, it's in the same menu right there. The most important and one of the most useful tool is temperature variation, those two, because if the simulation is right and everything, you can spot where there's air mixing, and if the simulation have problem, you can see them with that. When the simulation have problem, you have a lot of red. That is not a lot of red. It's just a little bit. It's everything is fine. Everything works fine. But if everything is not fine, what you will see, for example, code with a problem. So I have code. I go in 3D. Okay, in that case, the drawing is exactly the same like I made, but in the reality, the rack are lifted from the ground. So they are air going under the rack, and the containment doesn't, there's no blankets, there's nothing to prevent the air from going there. So what we see if we use that tool is that the model doesn't understand why you have a difference, and he tried to compute what's happening. If I put the temperature slice like that, we see that the temperature go really much higher than it should be, and we have red everywhere. Okay, because how we programmed the model is that he tried to find the mean on the input of the rack, and he tried to set the temperature. But if the temperature is not the same, there's an accumulation in the model and a mistake in the model. So that model is not good. It doesn't represent the reality. Why? Okay, the probe, if you use the probe in a reality and you draw that setup, that means that the probes are different than what it should be. So we see that in that containment, we have something that is not like we expect. What's happening in that containment? So I make another model right there. And in that model, we have the right value for the probe, and we have the gap just under the rack drawn right there. So I will zoom, and we have a small gap just there because we have wheels, but the wheels are too small, so it's not important for the model. If I click on a slice, for example, I look at the temperature variation. So we have a bit, again, a bit like I told for the first one, a bit on the inlet, but not that much. But what's happened is that we see we have right there, and at the bottom of our containment unit, and in close of the vent here, right there, we have air mixing, cold and hot. And if I go see the temperature layer on Z, I will pass all of them. We see that we have some of the hot going inside of the rack right there, and some air mixing there also. So if we put the arrow, we will see a bit more. So we have, okay, it's getting in, I think. So yes, we see the air getting under the rack and getting in the containment unit. So we can see what's happened, and when the CFD fail, it's not sad, because it means just that something is not like the reality, and you want to know that because you want to know what's happening. So that was a cold containment. I will take back our drawing that we just made, which I'm completely lost. Anyway, I will take a cold one, that one. And I will go in 2D. So we are in 2D, and I will convert it in 3D. So unlock. I will go in map editor. So I will first change my cooling unit. So now I want them to go from the ceiling to the front. So just that one right there. 75. Just put it 64 and 56. I make a new one. 64. Like that. Okay, and then the vent, I go on the floor. So we have a drawing of the floor, and I will put them back on the layers. So if I put them on the layers, they will go on the top of the containment. So that's our 3D drawing, and we see that we have our vents in place, but I forgot to put conduct on my cooling unit, so they are open like that. So that's why you have to look at your 3D drawing first. Let's go in layout. I can make a new vent, snap to object, like that. And like that. If I go in 3D, it should be on the top of my rack. Right there. See? Great. Everything should be good to start our simulation. So we are already at one that is running. It's doing the meshing right now. So it's doing the meshing. He finished the drawing, it's doing the meshing. He will start the model soon. So we will wait for that. Okay. Like again, I get the hot result and I show you the hot result. So let's start by showing you the hot, but with the vent that I forgot to put. Okay. In 3D. The problems are really more interesting because they are more interesting data to see. So we have our cooling unit that have no conduct. So if we go in, I will start with my trick. I will look at the temperature variation I, and we see we got red there, we got red there. So we see that we have a problem at that place. Maybe in the model or maybe in the reality, maybe the two disagree too. So you have to do a bit of investigation. But in that case, it's the model that's wrong because I didn't draw the right thing. So if I go look at the temperature on X, I see that I have some cold rendering there. If I click on airflow, I want the one in X. So yeah, we see that we got our air that goes back straight back in it. Great. Okay. So that's with a problem, but we will look at the right result. Right there. So if we look at the temperature, we will see less interesting thing happen. It's black and it's blue and red because we got the hottest inside and the coolest outside. So it's really far apart. If I hide the rack, we can see the airflow in the vent. Did it draw that one? Okay. Oh, I didn't take the right one. Here we go. So the airflow in the vent. And we can also see on the Z. That's not the right one. Sorry, everyone. On X, okay. Here we go. So we have our air circulation that goes exactly like we expect it to go. So it's a bit sadder. Yes. Okay. The trick is working really well to see the problem. On that one, I reverse the rack on the drawing. We see full of red everywhere because it should not be like that. So yeah, so that's about what I have to present. We have also on the website 2 demos that are already ready, cold containment demo and a hot containment demo. It's a bit different, but it's the same concept. So that's all for my part. Now, that will be Nicolas' part. Hi.
Yep. Just share my screen.
Oh yeah, we stopped mine. Okay, good.
Okay, so hi everyone. So what you saw there is a demonstration of the basics of the sensorCFD software. And as you saw, Gabriel used some arbitrary numbers for the kilowatts being dissipated, the heat generated by the cracks, and so on. So where the sensorCFD part comes in is where we take real life sensor data and we constrain that model using real life sensor data rather than arbitrary numbers. So the arbitrary numbers give you an indication as to how your data center should be performing, but the real life sensor data will give you actual what's going on. So if we go into the rack maps here, I'll show you how you create all of this afterwards. You would use our thermal map sensors to get the temperature at the front, top, middle, and bottom, and the rear, top, middle, and bottom of the rack, as well as the delta T. So you can drag the temperature sensor across to the correct location, and all of the others will automatically be positioned here. So some of you may be familiar with our thermal map sensors. So they use a single sensor port, and they will give you the temperature, top, middle, and bottom, front and rear. We also have the humidity, front and rear. These animated arrows you see going from one side to the other, that's the delta T value. So the delta T across the rack from front to rear, the temperature difference. So the quicker those arrows move, the greater the temperature difference is. And the color of them denotes whether it is in a normal or critical status. So at the moment, these sensors are not actually installed on a real rack. They're just sitting on a table in the office. So you can see the temperature at the front and the rear. It's basically the same. In a data center, you'd expect to see temperature at the front, say around 24, 25 degrees, temperature of the rear, 36, 37, up to 40 degrees, depending on how much heat and how much work these servers inside of the rack are doing. So this data becomes the plugin to the sensorCFD model. So rather than just saying, the temperature coming into this rack should be 24 degrees and the temperature coming out should be 37, we'll get real live sensor data. And every rack in your data center may be a little bit different because some racks will be doing more work than others. Maybe some racks have got servers in and others are full of networking equipment. So the performance of your racks is going to be different. So we can take this real live sensor data, plug that into the CFD model, and give her an actual picture of what's really happening inside of your data center and help you then identify places where you can potentially save energy. Traditionally, a lot of the sensors have been used to find hotspots inside of the data center, which is great. It's important to know where your hotspots are, but also as well, cold spots are places where you're overcooling, where you are wasting energy because you're cooling equipment that isn't doing any work. So that could be an indication of stranded capacity that you've got within your data center. So you could increase your capacity. And the sensorCFD can also help you then to identify places where you've got air mixing. So if you've got containment and you've got mixing air, sensorCFD is going to show that. And then you can begin to improve your containment and improve your whole data center setup to make sure that the air is going where it needs to be. So I'll show you how we set up these rack maps. So you're already familiar from Gabriel's demo how to draw these floor plans using our drawing tools. I'll just remove this from there. So at the end of Gabriel's demonstration, you basically are left with a floor plan. Now, this could be the demo floor plan that Gabriel showed, or it could be your data center. So once you've drawn it, you'll create rack maps. So here in AKC Pro Server, you'll go across to here and choose to add a rack map. And here you can create your rack map and enter lots of various parameters. So you can give it its name. Sometimes in data center, racks will be named after the rack number and the aisle. So it could be aisle 1, rack 1, for example. The short name for that, it could be A1, R1, or whatever you're using in your data center to identify the locations of your racks. Now down here, you can input the weight of the rack, the maximum load that the rack specification is for. So the manufacturers will say there's a certain amount of kilos that this rack is designed to be able to hold. The current load. So this could be taken from one of our current meters, but you can also enter an arbitrary value based on the specifications of the equipment you've got mounted in there. So if you have a bunch of servers and they are rated at 1 amp each, then multiply that by the number of servers you have. You can input that number here. And the maximum current load, this would be based on the electrical system, the breaker panel, and PDUs that you've got mounted in this rack. So let's say we've got a maximum current load of 32 amps. So once you've created that rack map, it'll show up here. So in the Server Explorer window on the left, you've got actual maps and then you've got rack maps. So with this rack map, we can drag and drop it onto our floor plan. So once you drag it across, it automatically knows you've placed it onto a rack and sizes it accordingly. If you just drag this onto another location on the map, it'll show up similar to our sensors. If we drag one of those across, see, they show up as a small icon. But if you drag a rack map across onto a rack, it'll show up like this. And you can see the rack there is named. So you could create multiple rack maps. You can actually create a data center. You see here, there's an add data center button. So this will quickly draw a data center for you. Now you would have to then put in where your core units are, where your vents are, and so on. But if you've got a lot of racks, then they're set out inside of your data center into a certain number of rows, you can set this up quite quickly. So we could go for a vertical grid data center. You choose the number of rows. So I have 5 rows and 3 columns. You can enter your room width, the height. So all of the information that you saw Gabriel doing earlier can all also then be input here. So you can choose to assign racks later. You can create new rack maps, or you can import the racks from a file. So if we go to create new rack maps, the prefix for the rack name, rack, and go to finish, it will actually create this map for you and automatically generate, you'll see down here, all of the rack maps that we need for that rack. And it's also kindly input a containment for us there. So this area here has no containment. So this could be network equipment or something that runs at a higher temperatures, and the area inside of your containment here. Then you can go into edit the map, just as you saw Gabriel doing before, and you can position your crack units and so on inside of this room, and you can run the sensor CFD. But what I wanted to show you just there really was how you can quickly populate a data center with all of these racks. And then you can drill down to one of those racks and you will be able to put onto it the sensor, just like we saw before. As I just made these, the racks might not have all been loaded up yet. So go back to here and drag our sensor back across. So in the Server Explorer window here on the left, we have our devices. So these are the AKCP base units. They would all show up here. And when you click on a base unit, it will show you the modules you have on that base unit. So this is an SPX Plus unit. We've got 4 sensor ports active, and you open up that and you can see which sensors are connected to it. So we have our sensor status light. You can drag that also onto the rack. So the sensor status light will show you the worst sensor status for the sensors that you've got connected to this sensor status light. We also then have the current meter, so you can drag this across as well. So the current meter is part of the sensors that you need for sensor CFD. So for the racks, we need the temperature, front and rear, and we need the power that the rack is using. So we have a sensor splitter box where you can connect the current meter together with the thermal maps and use a single sensor port. So say from an SPX Plus, you could cover 12 to 16 racks, because we have an SPX Plus with 16 sensor ports, and you could put a sensor splitter box on and cover all of those racks from a single SPX. And this current meter is non-invasive. So it clamps around a multi-core cable. So unlike a CT, where usually you have to get access to an individual wire, this current meter can go around a multi-core cable. So there's no need to split out the live wires from there. Doesn't need an electrician to install it. You clamp it on around the multi-core cable, perform a calibration procedure, and lock it into place. So it's not billable grade accuracy, but it's accurate enough for what we need for sensor CFD, and to give you an indication as to what the power utilization of the rack is. So this software, as well as being used for sensor CFD, can also be used for asset management and as a DCIM software for capacity planning. So you may see that I've got available space in this rack, but my current meter is saying that I'm already close to tripping my breaker, so I can't add more capacity to this rack, or vice versa. So we can also add assets to the rack as well. So this is a 42U rack. So when I mouse over it, you'll see all of the U's get highlighted. So we can add assets to this rack by going to add asset, and you can input then information on this equipment. So say this could be blade server number 1. You choose the type. This is a 1U, weighs 20 kilos, consumes 1.5 amps, uses 220 volts. So you can input all of this information here, the power source. So if you've got 2 PDUs inside of the rack, you can say, this is powered by PDU 1, and maybe then you've got other equipment in the rack powered by PDU 2, the date that this equipment was installed, as well as the time. You can also link this asset with a sensor. So we have SNMP get virtual sensors, so you could perform an SNMP get on the server to get current CPU usage or hard disk drive space capacity available. You could also create a ping virtual sensor, so you can ping this server and we can alert you if it's online or offline. You can also input other details on the equipment, the category, the manufacturer, supplier, the MAC address, the location, the building that you've installed this in. We can also track a maintenance log as well. So who's performed the maintenance to it, how often it should be performed, who the contact for maintenance of this is. So there's a lot of information you can input for an individual asset and then add it to the rack. So once you've created that asset, you can also choose to duplicate it. So you don't have to keep on doing repetitive work. So you can drag those into the rack. Once you've dragged it into a rack, you can drill down to those racks here in the Server Explorer to see what assets have been installed in those racks. You can also view the maintenance log. You can export all of the assets that you've got in that rack into a CSV file, so you can bring it into other software. There's a lot of features here, and this is only in the rack map feature of the APS. Yeah. So the AKC Pro Server software has a huge number of features. We could do several seminars just on this, but I'm going to focus on the things that are related to the rack map and how it ties in with the sensor CFD there. So we can now drag and drop across our thermal map sensor. It automatically locates it, and that's it. Once you go back to the 2D view, you'll see here on the rack map now, we have this gradiated color. So this is based on the critical and warning levels that you set for the rack. So if I say I want my inlet temperature to be 24 and critical will be 27, then because our front inlet temperature here, as you can see, the moment is 27, so it's critical. So we're highlighting this in red. So if this was in normal state, so 24 degrees, then you would see green at the front of the rack here. Now at the back, we've got the opposite. We've got blue, because our rack exhaust temperature should be much hotter than the inlet. Obviously, this isn't installed on a real rack right now, but if it was, you'd see that rear air temperature should be 36, 37, 40 degrees. So at the moment, it's showing up as blue because our exhaust temperature is too low. So that could be indicative that your servers are basically turned off or aren't doing very much work right now. If you switch to a 3D view, you get that same gradient on the racks there. And you can also see as well sensors that have been installed on the rack. So you see our rack map sensor there. And if one of these sensors is critical, you will actually see it here on the sensor. So at the moment, they're all green, which means that the sensor value is normal. But if one of these was critical, then you would see its color would change to red, or if it was in a warning status, it would be orange. So from the 2D view, you could see that you have a critical sensor, and from the 3D view, you can see which one of those sensors it is, which is in a critical state. And if you drill down to the rack map also, now we've added all this to the rack map, automatically we've got a desktop configured that includes a graph of the temperature at the front, the humidity, and all of the values of all of the sensors associated with this rack. So another nice thing in the 3D view is you can isolate an individual rack. So just by clicking on it, you can isolate that rack so it grays out the others, so it makes it easier to see, and it kind of ghosts the others as well, so you can see through. So if you've got a lot of racks in your data center, then you can use this to get a good view. Now you can also choose to view single racks as well, so you can click on a rack and it will pop it up. So we can click on another rack, it will pop that one up. So that's your single view rack, which also makes it easy when you're navigating a crowded data center to isolate an individual rack and see exactly what's going on with this particular rack there.
Hey,
You'll
Nick,
also, yes.
you taking questions or do you want to just wait?
I can take a question. Yeah.
Well, I was just noticing that the thermal map sensors are drawn to be in the center of the rack.
Mm-hmm.
In practice, that's not how they're done usually, though, right? And I guess.
Yeah, I mean, usually the cable would be routed down the hinge side of the rack, so that obviously the rack, the door can still.
Yeah,
be
I guess
closed.
my question then becomes: does that matter to the CFD calculations or not?
It shouldn't matter. I mean, the temperature at the front of the rack should be relatively even, across the whole front. If your containment's good, then the difference between the temperature from the center of the rack to the right or the left should be. Nothing to really consider.
Okay.
So another thing that you'll see here is that you can synchronize views. So we can actually create a desktop with 2 3D views on it and synchronize those. So I'll show you how that's done. So we can drag across onto here our server room map. And we'll put 2 of them on the same desktop. And we'll switch them both into 3D. So if we choose to synchronize views, when I spin one around, see the other one moves in the same location. Now, why would I want to be able to do this? Well, if we have sensors placed onto the racks, let me add a thermal map to this. I'll use the demo data center here, already set up. So I switch these to 3D, synchronize the views. Now, you'll see that I can choose to configure the rack air temperatures. I can isolate an individual rack. I believe you should be able to show as well. So on this one, I can choose to view a single rack. And the other view also synchronizes with it. You may choose to put different sensors onto here. So on this view on the right, you may want to put your water leak detection sensors or maybe your power meters. So if you find a particular rack in the data center, you can zoom in on this rack. And then on this view on the left, I can see the temperature, humidity values. And on the view on the right, I can see the power values for this particular rack, for example. So that's one use of this, synchronizing the two views together. You can also select this as well, which is called ASHRAE boundaries. So this shows you the ASHRAE recommended temperatures, and it will shade the rack based on the ASHRAE recommended temperatures. So ASHRAE is the American Society of Heating, Refrigeration, something engineers, and they publish papers on recommended temperature that you should run your data center at. So we've taken those recommendations and put it into a scale here. So you could see from this then which racks are operating within the limits of ASHRAE. So obviously you want them to be somewhere in the green, which means that your rack inlet temperatures, as recommended by ASHRAE, should be anywhere between 18 to 26 degrees. Now, obviously, the higher you can run your data center, the closer to that upper limit you can get, the less energy you're going to be using for your cooling. You can see here, because our rack inlet temperature is 27 degrees, we are slightly above the ASHRAE recommended, so we're out of the green area and into this orange area here. So on this view here, I get the ASHRAE recommended temperatures, and on this view here, I get the temperature gradient front to rear based on your AKCP thresholds. So this is the usefulness of being able to synchronize these views. If you imagine you have a very large data center, hundreds of racks, and you've found this one rack in one view, you don't want to then have to go and find it in the other view to see what the temperature gradients are. For example, they're synchronized here like this. So that's some of the features that we have there in this 3D mapping. You can also export these floor plans and import them to another APS instance. So that, as I say, is a very brief overview of what the APS can do. I didn't cover this action panel here, so this just gives you some basic information on the room. So it'll show you your average rack inlet temperatures, your average rack outlet temperatures, the maximum, the minimums, your dew points. You can also as well choose here to show ASHRAE boundaries. So rather than getting it through this menu here, you can also access it from here. You can also choose to show the air temperature, or the worst sensor status, or temperature only, or the humidity, or the front to rear pressure differentials if you have pressure sensors installed. So that's what this will do. It shows you the size of the room, the number of racks you have in it, the number of vents you've got. So it's all of the data basically on the data center that you've created here in the software. So one other thing that I'll show is for sensorCFD, it's ideal obviously if you're using the AKCP sensors. You've got the thermal maps installed, you've got temperature top, middle, and bottom. The more sensors you have, the better we can constrain the CFD model, the more accurate it will be. But you can also use our virtual sensors. So under add device here, you can create virtual sensors. This could be an SNMP get virtual sensor. So if you have already a PDU, which is an intelligent PDU with power metering in it, then you can create this SNMP get virtual sensor. You can get the power readings from that intelligent PDU, and that can be used as the power input to the sensorCFD model. Some PDUs also these days come with a single temperature sensor that you can put on there. So again, you can do an SNMP get those temperature values and use that as the input to the sensorCFD. It's not going to be quite as accurate because you've only got a single sensor and you don't have the front and rear and so on. So it's much better if you use the thermal map sensor. More sensors you have, the more accurate it will be. But it is possible for you to purchase virtual sensor licenses for AKC Pro Server and use those to bring in data from sensors that you already have. So your options for sensorCFD is, you can run it with arbitrary numbers as a traditional sensorCFD, and that's completely free. You can purchase virtual sensors, and you can bring in data from sensors you may already have. And you can also then purchase the AKCP sensors to get kind of, full accuracy on your CFD model. So if you have any questions about the APS, I'd be happy to take them, or show any other features. I know some of you are familiar with the software already. You may have some questions about something not related to sensorCFD. I'll see if I could answer that for you now.
I have a question about, you mentioned that you need the current to run the CFD model.
Yes, the current, the power readings of the
power readings. Yeah. So I don't remember Gabriel showing the power when he did his model. Is that required, or is it just recommended, or?
I believe it's required. I think, Gabriel, we have to have the temperature of the rack and the power, yeah?
Yeah. We have either the power or the air velocity, because we have to compute the air velocity. In more traditional CFD, so that CFD that we added there it's a snapshot. We kind of call that a steady state. So it's take one moment. Usually, when you want to model for changing your room and placing your rack, you do what's called transient. And in the transient, you just set the power of the heat that your rack produce, and the rest is computed and yes, computed by the airflow. In your case, the rack bound the model, so we have to have the information about the air exchange of your rack. So yeah, we need either the power or the air velocity, but the probe for the air velocity are more expensive, so you will give the power.
So I guess I just didn't understand how power affected air circulation. So
well, to calculate the air velocity, I believe we do it from the power reading and the temperature, and then we can calculate the air velocity through the rack based on the amount of power that's being dissipated.
Okay, so if you had a data center like the one modeled here, and you had a rack, and you wanted to say, you mentioned earlier, like, okay, I have some space in this rack to add a few more servers. I have enough power, but without actually putting the servers in, how would you model that to see if it does anything to the CFD calculation? Because the sensors aren't going to pick up the servers unless they're actually in the rack.
Yeah, that CFD is not made for that. Yeah, like I told you, you have two kind of model. You have transient model and you have steady state. That one is a steady state made to work with the probe. So
okay, gotcha.
Yeah, so if you wanted to do a kind of projection of what it may be,
like a what if, yeah, right?
Right, yeah. So if you use the sensor data, that's what you have now. If you do what Gabriel did, which is input values, manually input values,
okay,
then you could use that as a projection. So you would say, okay, this is what my data center is now. I want to add two servers to this rack. These manufacturers stated, power consumption of these servers is 1 amp each. My rack's currently using 4 amps, so you would input 5 and then run the simulation on that. Yeah. But if you wanted to add a whole new rack, then yeah, you could take your current floor plan, you can put a new rack into there. And I'm not sure on this, Gabriel, this would be a question actually. So if I had sensors on all of these racks that I currently have, and then I want to do a simulation and I'm going to add a rack that obviously I have no sensors for. So can I input manual data for one rack, but use sensor data for everything else?
Yeah. You can mix them up, but the accuracy of your model will lose a lot of you will lose a lot of accuracy in your model. It's not a model made for projection. It's made for seeing what's happening right now. Yeah.
Does that answer your question? Yep, go ahead.
Yeah, Nicholas, for your floor, for the server room model map that you do, most server rooms are on a single level, but server rooms that are put in multi-level buildings, multi-floors, have columns in them. Are you able to add physical floor to ceiling columns in your model and then model the airflow around them?
Yeah, I'll let Gabriel share his screen again. I think, Gabriel, you showed this in the last presentation you did, how you could add a beam or other physical elements of the structure into the model.
Yes. I can share the screen. Did you just share the right one? Okay, that one. Here we go. So everybody should see my screen. I just try what Nicola said with sensorCFD. I didn't know that we can do that. Okay. I will go back here right there.
Yes, that was another nice use of the synchronizing the two screens. You can have two different views of your sensorCFD and synchronize them together.
Yeah. I just got I just learned that we could do that, so I tried it. Okay. We have some other tool that I didn't show. So for example, I show a map with a rack raised because we can raise the object. If we can go in edit there, we can change their position in Z. So the drawing tool is in 2D, but the simulation in 3D. So you can stack the rack, you can make two floor, you can add beam like that. Right there, we have box. Box can represent a beam, a desk, about anything. So it's a box. So right there. So you can cut the space, put the beam on the roof. I will just do that right now. So for example, we have a retail and 8. So 5 meter of 8. So the two other will be set when I draw them. There and lift it. So for example, I think it's 2.5. No, it's too high. 1.5. So yeah, you can put a beam. You can put it under the floor. You can put it on the roof. You can put it where you want. So that represents an object. If, for example, in that one. Oh yeah, I forgot that time that kind of view. But yeah, you can just use box, and box make your beam make your beam like that, or a desk, or anything that takes space, really. So obviously you have to do the model because the old data is not good, but yes, you can.
All right, thanks.
So any other question? So if there's no other question, I think we can wrap it up. So what I just showed today is it shows in beta, so you will find some bug probably if you run it. If you need help or you run into a bug, you can go on our forum on AKCP.com, support user forum, and put your question, put your problem. Sometimes sometimes some things won't work, but it won't be you. It will be a bug you found. So we will fix it. And we already adding some function that some user asked. So yeah, just feel free to ask things that missing, or if you find a problem running a model, just go on the forum, and or you can also send me an email or Nick email, and we will help you. Just little before closing it, if you use cloud computing, don't forget to destroy your server or close your server, because they are billed by the hours. So so if you forget to close them, it will be a bit expensive, because it costs about $1 an hour. So it's not that really expensive, but if you forget to close it, it can get extra expensive. So thank you all. I hope that you liked the presentation, and that you try. And Nick?
Thank you, Gabriel. Thanks, Nick. Appreciate it.
Thank you, everyone.
Thank you.
I'll upload this to YouTube, and it'll be available there for you to, if you want to review anything. All right.
Awesome. Thanks.
Okay. Thanks very much, everyone. Bye-bye.
Bye.